Okay, this introduction says that before putting their walkathon plan into action, the Slow and Slothy 7 were curious as to how much money had been donated to cancer research in the past. They found this following graph that deals with the years of 2001 to 2007 and then looks at the donations in thousands. So only question we have to do on this intro is just write a paragraph explaining the amount of yearly donations between those years of 2001 and 2007. Might seem kind of strange that we're writing in math, but this is one of those sections where we are going to be doing a lot of writing and interpreting of what this graph means. So the first thing that I notice is that this graph is kind of split up into three different sections. I see between 2001 and 2002, we had a decrease. So maybe that's the first thing that I'm going to say. There was a decrease or a drop. Maybe that's a better word because decrease is more math. There was a drop in donations between 2001 and 2002. Okay, we went from just above 40,000, dropped down to maybe like $35,000 in donations. Okay, that's the first section. Now I'm going to look at the second section here, and I realize not quite constant, but pretty darn constant, and that, if we were looking at a slope, has a pretty high slope. Okay, we're just explaining the yearly donation, so I'm not going to really put any numbers in there. I'm just going to explain, just as a quick interpretation, what happened. So we had a drop, but then all of a sudden, we have a pretty good increase between the years of 2000 to 2005. But the years between 2002 and 2005 were very good. With a big increase in donations. Okay. Now, last little section here, I'm going to look at between 2005 and 2007. Notice we're still increasing, still not quite linear, because we have a little bit of a jump right there. Increasing, but by not as much. So that's the very last thing that I'm going to say. So let's try the donations. Still increased between 2005 and 7, but not as much as the previous years. Okay. As a side note, I do apologize for my handwriting and not making excuses for myself, but it's hard to write on this thing. Okay, so again, that's what we're going to do. We're writing. We are going to analyze and interpret a graph. Looking here, we did look at the increase and the decrease. We're going to go back and look at the intercepts, which is what we've already done. We're going to look at the extremas, where we're looking at the lowest and the highest rates of this. So our lowest would be in 2002. Our highest for the time being would be 2007. And then we're also going to be looking at the end behavior, where if we look at this, what do we predict in the future? Well, we're predicting that we're probably going to keep increasing. So not very much math at all. It's more analyzing a graph and learning a little bit new vocab. So go ahead and get out the notes and vocab for this section. The objective of this section is to interpret key features of graphs in terms of quantities. And here's a whole bunch of review vocab. To interpret the graph of a function, estimate and interpret key features. The intercepts of a graph are points where the graph intersects an axis. The y-coordinate of the point at which the graph intersects the y-axis is called the y-intercept. Similarly, the x-coordinate of the point at which a graph intersects the x-axis is called the x-intercept. So again, this first one is more review than anything. One thing that we haven't really talked about graph-wise is looking at linear or nonlinear. We looked at it in equations. This is almost easier because we can just visually see this. The graph shows the height y of an object as a function of time x. We are supposed to identify the function as linear or nonlinear. Then we're supposed to estimate and interpret the intercepts. Okay, again, we can visually see. Can we put a ruler on this and can that ruler touch every single point? No. So linear or nonlinear, we are going to say nonlinear. Okay, then we're supposed to estimate and interpret the intercepts. So y-intercept, I look at this y-axis, I go straight down, there it is. Okay, that hits probably at about 15. Okay, so we're going to say that the y-intercept is about 15 meters because that's what we're dealing with is height in meters. Then we have to interpret that. Well, let's go ahead and look at what we're dealing with. We're dealing with time and height of an object. So it looks like this object started at 15 feet and it was launched up in the air. Okay, so we're going to say at the start of the launch, that's what I'm going to assume is happening, the object was 15 meters high. Okay, and I did use the word start because that kind of shows me that time is 0. So there was my clue word that time 0, I was at 15 meters high. Now I'm going to look at the x-intercept. Again, I'm going to go across the x-axis. There it is right there. Down here, we're going by ones, so that's about 7.3-ish. So x-intercept, 7.3, and we're dealing with time in seconds. So what does this mean? Visually, this was launched at 15 meters up in the air. It was coming down, and height is 0 now. So it reached the ground. That's the clue word that I'm going to use about the 0 at about 7.3 seconds. So I'm going to say the object hit the ground around, and I'm going to say around 7.3 seconds. Okay, notice that it started at 15 meters, but here it actually hit the ground. It didn't hit the platform or whatever it was to start with. So clue word ground, and then I interpreted what that 7.3 seconds means. Okay, so go ahead and try that for guided practice 1. Okay, I really like these examples because they're about as real world as it can get. So again, first thing that we have to do is look at whether it's linear or nonlinear. Yes, we can put a ruler on this and it will hit every single point, so we are going to say this is linear. Then we have to interpret those intercepts. Y-intercept is actually at a negative position right here. So I'm going to say -5 degrees Celsius because we're dealing with temperature. What does that mean? It means that at the beginning, so there's my 0 time of the experiment, the sample was -5 degrees Celsius. Now looking at the x-intercept, not very far away, but it's right here at 1 what? 1 hour. So again, interpret that. What does that mean? It means 1 hour into the experiment, the sample was 0 degrees Celsius. Okay, just interpreting what that graph means, putting it from a visual form into a written form. All right, line of symmetry is the next step. The graphs of some functions exhibit another key feature, which is symmetry. A graph possesses line of symmetry in the y-axis or some other vertical line if each half of the graph on either side of the line matches exactly. So that means that we can fold it on top of itself. Okay. So visually, can we take that? Can we fold the piece of paper and both sides line up with each other? Fold on top of itself and sides line up. Just kind of a visual check. So let's look at real world example 2. It says an object is launched. The graph shows the height y of the object as a function of time x. Describe and interpret any symmetry. Okay, first off, we have to look at this and see if there is a line of symmetry. Can we take this graph and fold it so each side lines up? Yes, we could. We could fold it probably right here. That would be our line of symmetry. Okay, so we're going to say that there is a line of symmetry at about 2, 3.5, and we're dealing with seconds, at about 3.5 seconds. We have to interpret that, though. So we're only halfway done. So again, we're looking at a height of a launched object. We started at 0, 3.5 seconds, it reached its peak, and then it came back down at 7 seconds. So what does this line of symmetry mean? This means that it took the same amount of time going up as it did going down. Okay, that this means the object took the same amount of time going up as going down. Or and, maybe that's a better word there. Okay, line of symmetry. Can we chop it in half? So let's go ahead and look at guided practice 2. Okay, hopefully you looked at that and didn't force a line of symmetry out of that. You could realize right away that there's no way. Again, we're looking at vertical. Could I chop this in half and have them line up with each other? No. If I folded that, this piece would be over there, that would be over there. It does not work. So no line of symmetry there. Okay, this next graph is kind of overwhelming, but it's amazing. The amount of information in this, if you are working on a section like this, I would highly recommend printing this out and having it right beside you, because with this, you can do anything. So interpreting a graph also involves estimating and interpreting where the function is increasing and decreasing, positive or negative, and where the function has any extreme of values, either high or low. So again, 4 different sections here. Positive and negative are different than increasing and decreasing. Positive and negative, I always look at this as a lake. What part of my rock is poking out of the lake? Right here. So this is the positive part and this is the positive part. Which part of my rock is under the water? There's where my negative values are. Okay, so the values of your y, if we were going to plot this point right here, this would have a negative y value. This would have a positive y value. So understand that's what positive and negative mean. Increasing and decreasing is when I jump on my skateboard and I try to figure out what's happening. If I start left to right, here I'm going down a steep hill, and then all of a sudden I have to push myself up a hill, and then I'm going back down that hill. So always start from left to right. What's happening? I like the fact that they color code this, and that is a good idea. Color code in the different senses. Okay, you might have to do that 4 different times because we're dealing with 4 different things, but decreasing, I am turning around, I'm increasing, and now I'm decreasing again. Okay, now we're looking at extrema. The points shown are the locations of relatively high or low function values called the extrema. So the highest point and the lowest point. Point A is a relative minimum. That is the bottom of my swimming pool. And then point B is a relative maximum. It's the top of my mountain. Okay, or you could see this as a mountain in a valley. Okay, this is my valley, this is my mountain. That again is different than end behavior because the relative min and max are inside the graph. The end behavior is what's happening with those arrows at the very end. And this is where you almost have to write a sentence. End behavior describes the values of a function at the positive and negative extremes in its domain. So many times you're going to say, as you move left, the graph blank. Okay, as x decreases, y something. So these, you're always going to use this sentence, and I like that as x decreases, y something. That word is either going to be increases or decreases. Okay, as x increases, y does what? Okay, so use this sentence right here. The only word that you're going to have to change is what is y doing. Because x is always, you're always going to go left and you're always going to go right. It just depends on what your graph is going to do. Okay, so to help you out with that, use this sentence and just fill in the blank of y is doing what. And we'll look at that in this next example. Okay, I think this is actually the only example we have, but look at how many pieces we have to it. So here we go. It says the U.S. retail sales of video games from 2000 to 2009 can be modeled by the function graphed at the right, where we have years and we have the retail sales in billions. That's crazy. Estimate and interpret where the function is positive and negative, increasing and decreasing, the x-coordinates of any relative extrema, and the end behavior of the graph. Okay, so we are going to look at positive. And again, this is where our sales are positive. So when is that? We're going to look at this. All of this iceberg is above water. Okay, and this actually, even though this goes into the negative, this is still positive right here. So when is this positive? We're going to say between about negative 0.5 and about 10.2. Okay, but what does that mean? We're supposed to interpret that. That means negative 0.5, since we're dealing with years since 2000. Okay, we're going to say in the middle of 1999. Game sales started picking up. And remained positive until when? Until 10 years later, until the middle of 2010. Okay, we're going to explain that later, but that's what it means. Okay, so 1999 we started seeing positive sales until about 2010. So a pretty good 10-year little stint there. Okay, negative. When is this thing negative? All right, we're looking at this right here and right here. So if it's positive between these, it's negative before negative 0.5 and after 10.2. So what that means is that video games sales I'm going to use some big words here. I'm going to say started flourishing in the early 2000s. But began its decline and started seeing bad sales around 10 years later. Okay, Hopefully you agree with me. Again, that's basically what that means. Started seeing that popularity in the 2000s that had that nice 10-year stint, and all of a sudden now we're declining, bad sales. We might have to close up shop. 2010. All right, increasing. Let's go ahead and look at that. So I think I'm gonna leave those, but we're gonna look at how this increases. Changing colors. Let's try green. So increasing. When am I pushing up on my skateboard? All of that green. All right, decreasing, starting to crash right about here. So let's describe that, interpret it. We are increasing at about -1 to 8, which means sales were good. Between, again, what's -1 as a year? Well, that means that it's 1 year before 2000, between 1999 and 8 years after that, 2008. Okay, decreasing from 8 to 10. What does that mean? Same sales. Slowed down and began declining. In 2008 and continued through 2010. Okay, so about halfway done. Look at this. We've got a couple more here. Looking at a relative minimum now. Relative maximums and relative minimums. Okay, hopefully that's not small enough that you can't read it, but I'm kind of running out of room here. Relative maximums, the highest point of our little peaks. Notice that we actually have two of those. We have a maximum here. There's our highest peak, but we also have a little small peak right down here. So we have two of them. Looking at a relative minimum, where's the valley of this? Well, actually, it happens right after our little peak. So we have to explain this. Our relative maximums, we're going to say around, what is that at x? Around about 1.5. And highest peak, 8. Relative minimum is right at 3. So I'm going to say around 3. Okay, so now let's go ahead and interpret this. What happened? So we're going to say that sales experienced a peak, and we can even use that word, in the middle of, because we have 1/2, 2001, and in 2008, with sales of, because let's go ahead and look at the sales. Sales of, I would say about 10, because this is 8. And so this would be 12. Yep, so I'm going to say about 10 and $22 billion. I like the word respectively. Okay, so those were definitely good years for them. And then with a low year in 2003 of maybe 9 billion. Okay. a lot of work on these type of problems, but that's what we're looking at. I mean, we are pulling this apart. I'm going to change that color because that's what I'm dealing with. Okay. Business people do this a lot. I mean, they look at that and they don't just number crunch. They look at those and understand what's happening. Okay. End behavior is dealing with something just a little bit different than that minimum and maximum. So this is where anytime you're dealing with end behavior, I always start with when X increases. What colors have I not used? I don't like red, but I guess we're going to have to. Okay, so when X increases, Y blank. When X decreases, Y blank. Now we have to go up here and look at this thing. Okay, when X increases, when X gets bigger, Y is doing what? Well, that arrow is going down, so we know that he's decreasing. When X decreases, when X is getting smaller, what is happening to our Y? Arrow is pointing down. So actually both sides, Y is decreasing. Okay, so what does that mean? That means that sales before 2000 were not good. Sales after 2010 were not good. In a nutshell, that's what it means. So that's what we're going to write. Sales before 2000 and after 2010 were not good. Okay, we pulled this graph apart and analyzed the heck out of it, but that's what you do when you interpret data. You have to number crunch these, look at it, explain what happened. Okay, business people, this is the story of their life. So go ahead and try that with guided practice 3. Okay, looking at our little experiment of thawing a sample from the other guided practice. So looking at positives and negatives, again, that focuses on that x-axis. So all values greater than 1 are positive. All values less than 1 are negative. What does that mean? That the temperature was below 0 until the first hour. That's how we interpret that. Increasing and decreasing. I set my skateboard right here and I am constantly pushing uphill. So all values are increasing. No values are decreasing. What does that mean? That as the day goes on, the sample continues to get warmer. There was no part where they stuck it in the fridge and all of a sudden it decreased. It is continually getting warmer. Looking at the relative maximums and minimums. If you can quickly see that this is a linear function, you're not going to have any of those. So again, there is no relative high or low. Please don't look at these arrows as relative highs and lows. That's end behavior. End behavior deals with arrows. Relative maximums and minimums, extremas, deal with valleys and peaks of mountains. So none. And that's what I said. Since this is a constant function, that it is constantly getting warmer, there are no extremas. And then end behavior. I started with as x increases, y something. As x decreases, y something. Because x's are independent. So looking at that, as x increases, I look at my arrow. He's pointing to the sky, so I know my y increases. As x decreases, gets smaller, I look at my arrow. I know that my y is decreasing. And I stated that as the day goes on, the temperature increases. Basically kind of tells us the same thing as they're increasing and decreasing. So these problems, they do take a lot of time. But again, this is a story problem. This is real world in a nutshell, that looking at that graph and pulling it apart to understand every single piece of it is important. And now you are ready for the assignment.